Okay, welcome to video 2 from our lecture series from Monday, March 13th. We are going to kind of warm ourselves up to the idea of molecular orbital theory by looking at what's known as a molecular orbital diagram for elemental hydrogen, or homonuclear diatomic H2. So when we look at this molecule, we're trying to use this warm-up as a means of exploring what molecular orbitals are going to be formed as a result of each hydrogen atom's atomic orbitals combining. And as a result of those MOs being formed, where are electrons then placed? So the way that we draw molecular orbital diagrams is we start like we would normally start with any kind of orbital diagram or orbital box diagram by writing an energy axis. And I like, when I'm drawing my MO diagrams, to, of course, I'm going to place each of my elements that are involved in my molecule kind of like to the left and to the right. And then in the middle, I'm going to show the actual molecule that's being formed. So we can consider this like the hydrogen 1 and hydrogen 2 coming together to create H2. And as I was saying, I like to start out my MO diagrams by writing out the electron configuration for each of my elements that are involved. So I know that hydrogen has an electron configuration of 1s1. Now, what does this mean for me in terms of my MO diagram? What this means is I'm going to be looking at linear combinations of my 1s orbitals. And as a reminder, when we look at s orbital combinations, we have two combinations we can look at. We have the additive combination or the constructive combination, which gives us a sigma s molecular orbital. So this is like if we were to just take these two orbitals and add them together, like so. So if we've got S and S of the same energy, we create a sigma sub S MO. And we can also look at the kind of anti-addition, the subtractive interference, the destructive interference, subtractive combination of our s orbitals. This creates a shape kind of like this. Where s orbitals are kind of blown apart. We generate a node or a region where no electron is going to be found, and this creates our sigma s antibonding orbital. So this up here is our bonding molecular orbital, and this down here is our antibonding molecular orbital. The bonding molecular orbital is always lower in energy than our original atomic orbitals, and the antibonding is going to be higher in energy. So let's put this together in our MO diagram. So I'm going to start by drawing, instead of boxes, just lines that are going to be placeholders for my atomic orbitals. So this is going to be the 1s orbital from each hydrogen atom, placed directly on top of what atom is contributing that particular atomic orbital. And since I am looking at a combination of my 1s's, I know I'm going to be forming these two molecular orbitals. So I'm going to form my bonding orbital, my sigma s bonding orbital, and then my antibonding orbital, sigma s star molecular orbital, where we have again this lowered energy or more stable bonding orbital. And let's remember, the reason why anything bonds together in the first place is because it's trying to be stable. So we should show bonding orbitals as being more stable than the respective starting atomic orbitals that made them. And then higher in energy is going to be our antibonding orbital, like so. And we're going to connect these orbitals to their parent orbitals, aka these 1s orbitals that made them, just to show where they came from. Okay, let's start filling in electrons. So just like I would in any other orbital diagram, I'm going to use half arrows to represent electrons. So if I'm looking at my 1s1 electron in each hydrogen, I could draw it like so. And now I'm going to take these 2 total electrons that I have to build my molecule, and I'm going to fill following my Aufbau principle from low to high, meaning I've got to completely fill my lower energy before I can move on to filling my higher energy. So each orbital, again, can hold a maximum of 2 electrons. So if I'm going to place these 2 total electrons now into my molecular orbitals, I'm going to have to, starting low from high, place them both into my sigma sub s bonding orbital. And that's it. This is the molecular orbital diagram for hydrogen. So let's go ahead and answer these questions. What molecular orbitals are formed? We form the sigma s and sigma s star molecular orbitals as a result of our s atomic orbitals combining in a constructive and destructive head-on manner. And then this second question, where are the electrons placed? So we see that we have an electron pair placed in our sigma s bonding molecular orbital. And I would hope so, because we know that H and H, according to Lewis, form a single bond between them. Now, of course, MO theory is not exactly comparable. This is saying that we've got bonding electrons in this region around H2. So this is our sigma sub s bonding orbital. And so our electrons are now placed in a region that is around the entire molecule and not just localized in a single little bond like we'd expect from Lewis or valence bond theory. But in general, it makes sense that we would have electrons in a bonding orbital because we do see hydrogen bonding to another hydrogen atom. So this is the basic structure of an MO diagram. You start with each of your elements flanking the molecule that's to be formed in the center. You draw in your atomic orbitals to be combined and then show the results of those combinations connected with dashed lines. And I like to, as I said, draw in my electron configuration beneath each of my elements that are coming together to create my molecule, just so that I'm super clear about what orbitals are going to be coming together and what orbitals contain what number of electrons, so then I can place them appropriately in their resulting molecular orbitals. So in our next video, we are going to look at a little bit more of a complex example. So we're going to look at some more homonuclear diatomics, specifically molecules like oxygen, fluorine, and diatomic neon. And then we will talk about a little bit of a deviation from the pattern we'll see there by discussing this notion of sp mixing.